Hello, and welcome to the lecture on life in the universe. Here we're going to talk about the search for aliens, where we might find them, and all that good stuff. Okay, so do we think we're alone? What is our place in the universe? How do we explore for aliens? These are the types of questions we're going to ask here. And when we think about life, we of course think about our own planet and how life may have originated here, how long has it been around. And then we look at one of our nearest neighbors, a planet that, for all purposes, for all evidence, seems to have at least supported liquid water in the past, and this is Mars. And so, what's the story there? Was there once life on Mars? It's hard to say for sure. And then we look more distant in the solar system, and we see these particular types of moons. We'll talk about two main examples. These particular moons around the gas giants. In fact, three examples. Two that fall into this icy moon category. And then we'll also talk about a moon that isn't icy, but also is just makes you wonder about different types of life, different paths that life can take, because those are those are extremely varied. There's not just one path for life, even here on our own planet. And then we search for life in other worlds, and that obviously is a difficult task. How do we analyze the tiny amounts of light that we can detect from exoplanets, and how do we gain some information about whether those exoplanets might support life? Right, so these are the types of questions that we'll be asking in this chapter and in this lecture. Okay? So here we see a picture of a comet. This is the Hyakutake comet. And looking at it, it makes us think about comets in general, because comets carry a huge amount of water, and they also carry a huge amount of complex molecules that are the building blocks of life. So, although they don't, as far as we know, have microbes on them, they certainly seem to have those same common chemicals. And this not just hydrogen, not just H2O, but other carbon chain chemicals. So it makes you wonder that perhaps comets are important for seeding life on worlds. Perhaps they were important for seeding life on our own world. And certainly when we think about the sheer number of collisions of comets with Earth, especially early in Earth's history, shortly after it was formed as a planet, the amount is huge. And some think that the entire oceans can be attributed to comets. That there wasn't very much liquid water on the planet during its formation. It would have evaporated away, and the water came later through comet collisions. So here we have a baby. And the reason we have a picture of a baby is just to appreciate that we're even thinking about this. That we are a species that have evolved on one planet around one particular ordinary star that looks back at the universe and questions it. It is the universe becoming aware of itself in us. Is that a unique phenomenon in the billion stars in our galaxy, the 100 billion stars in our galaxy, and the hundreds of billions of galaxies, each with the hundreds of billions of stars? Well, probably not. Okay? But it's so interesting. A universe that can start with just hydrogen and a little bit of helium and then end up questioning its own existence. Amazing process, isn't it? Now, I mentioned those molecules in comets and how it's just such an important story, thinking about the comet bombardment on a planet like Earth, and those complex molecules that are in such abundance in the huge amount of comets that exist in a typical solar system, as far as we know, comparing our solar system to others. So that's not the whole story, though, because if you remember our discussion on interstellar gas, you probably recall that we talked about the type of gas that cools and contracts into stars, that creates those stellar nurseries. And that type of gas wasn't hot ionized hydrogen gas. No, not at all. It was cool molecular gas, because that type of gas is able to radiate heat away and actually collapse under the influence of gravity, eventually forming a protostar. But we mentioned that scientists were surprised at the molecules that exist, the complex molecules that exist in those clouds. And the reason we should consider that in this discussion of alien life, life beyond Earth, is because that's a lot of complex molecule. The sheer volume of interstellar gas, full of so many molecules, gives credence to so many opportunities for the building blocks of life. They're not rare at all. They're in incredibly huge abundance. Now, obviously, some of those molecules are going to get trapped inside of stars, but others will get left behind in the comets, in the leftover little pieces that are so important for a small leftover little world like ours. Of course, referring to the fact that our planet itself formed from the aggregation of leftover matter that didn't collapse into the star in its formation. Okay? So much building blocks out there, so many molecules, so many opportunities for life to start. But does it? Well, we know for sure it started once. That's all we know. That life, for sure, based on our limited amount of knowledge here, stuck on Earth, in our own little gravity well, in our own little solar system, we definitely know that there's life. We're part of it, of course, and we have some idea about where it first started. And there's one organism that left a telltale evidence of itself way back 3.47 billion years ago. And those are an interesting type of bacteria called stromatolites. All right? Now, stromatolites are not the only life form that probably existed 3.75 billion years ago, but they're one that left direct evidence of themselves because they formed thick mats, and those mats show up in the fossil record. And we can even see stromatolites that are just a few thousand years old in the coasts or off or on the coasts of Australia. And there we know for sure that there was life way back early in Earth's history, and that it began in harsh conditions because the Earth 3.75 billion years ago was nothing like the Earth is today. There was no oxygen in the atmosphere. There would have been much less liquid water, much less. There would have been much harsher conditions for life, but life found a way. And again, as I mentioned, there certainly were types of life that didn't leave evidence, right? Because not all types of bacteria form thick mats that kind of take on a bony nature and then can get left behind as fossils. That's rare. There was probably plenty of more ephemeral organisms that left no record because they were just little slimy things that disappeared once they died. Their chemicals recycled back into the oceans that life was in, because at this time there would have been no terrestrial life for almost a billion years after the first life formed. So we see that there's a saga here on Earth. Now, how did it start? We're not sure. And why didn't it start earlier if Earth is 4.5 billion years old? Well, because early on, life was bombarded too much by too many giant asteroids, too many planetoids, too much heating up of Earth's crust, too much of Earth remaining in an almost perpetual molten state, even on the surface, and it was just too inhospitable. That said, perhaps even then, life was starting. Scientists theorize that maybe in that early process, life was getting bombarded into space, surviving in stasis on rocks that eventually collided 1,000 or 2,000 years later back into Earth's gravity. It's remarkable to think about. Little pockets of liquid water on an otherwise molten lava world. And that's how life would have been way back then. And if that's the case, if life could have existed in an early primordial Earth, then life can exist just about anywhere, right? Well, there's actually even more to that story. Because life as we see it on Earth is incredibly, and I can't overstate this, incredibly tenacious. The more we study life, we see that as long as there is a movement of nutrients, then life seems to find a way. So it's almost all we need are the nutrients and a cycle for those nutrients. Just some kind of mechanism so that it's not completely still. Because you think of a world that is completely frozen, completely rigid. There's no opportunity for life to form because there's no mixing. There's no processes that can lead to self-replicating molecules. Because ultimately the building blocks of life that we understand, and we have biological molecules that aren't life itself that exhibit the mechanisms of self-replication. And so that needs a flow, it needs movement. There needs to be nutrients, and to get the cycle, you need energy. Okay, so you can't have a lack of energy. But in any environment where there's nutrients and energy, we seem to find life. Now on Earth, there's one other ingredient. There's always water. So nutrients, energy, and water, and we have life. And to maybe illustrate that point on a big scale, and then we'll illustrate on a couple specific scales, this fascinating figure of Earth shows chlorophyll concentrations that are associated with areas where there's more organisms. More organisms mean more chlorophyll. Chlorophyll comes from photosynthesis. If there's more organisms undergoing photosynthesis, then there's a more robust food chain that then supports other organisms that don't undergo photosynthesis. Therefore, chlorophyll is an indicator of all forms of life. So we see that in Earth's oceans, we have regions where there's lots of life. And it turns out that those regions where there's lots of life correspond to the northern seas, the southern seas, and a little bit right along the equatorial seas. Not so much in the middle latitudes. And that can really be attributed to one abundance, which is nitrogen. Because the nitrogen is a building block. And without it, certain important molecules can't be easily made that then lead to life. And so there's less life where there's less nitrogen. See how important the chemicals are, the nutrients. Nitrogen is one of those nutrients. And it's actually just a fascinating fact on a biological, ecological level that it really is the southern oceans and the northern oceans, the colder oceans of the world, where there's more life in the sea. Things like lobsters and crabs, you don't find them in these middle latitudes. You find them in the far north and the far south. Those are considered the life-giving oceans. Even though they're so frigid and so undesirable for swimming, they're so desirable for life. And for one reason, nitrogen. Now, here are the specific cases of just how life has been shown to be so remarkable here on Earth. We see that life can exist in boiling hot springs. Okay? We see life can exist in hydrothermal vents at the bottom of the ocean, miles underneath the surface, incredible crushing pressure, boiling hot water. This looks like smoke, but it's boiling hot water that is dyed by thick amounts of minerals in the water. And look at these. These are all mollusks that are growing. And there's crabs that live in the mollusks, and there's bacteria that start this food chain. And this food chain, these hydrothermal vents, are rather famous in the astrobiology communities because here we have an ecosystem that appears to function completely separate from the energy of the sun. Take note of that. Completely separate. These organisms don't survive on nutrients raining down from the ocean above, from organisms that rely on photosynthesis. We have organisms that are completely absent from that chlorophyll cycle. No photosynthesis to start the food chain. Not at all. Now, these organisms are rather rare, which is why they don't dominate our global picture here about where we find organisms, but they do exist in the right conditions, rare or not. And where they exist, they get all their energy starting from chemical processes in the vent itself. The vent itself is the source of energy. Therefore, the source of energy is the cooling and radioactive core of our own planet. We don't even need the sun. These organisms could exist and would have existed for billions of years if our planet had been flung out of the solar system and was in deep space with no sun. The only issue there is that we would have a frozen over ocean. So then there would have to be enough, so then we would have a frozen ice surface on our oceans and only water at the very bottom. But that would not exclude the possibility of life like this existing at the bottom of that ocean underneath a thick ice sheet. Because there would still be energy coming from the core of our planet. Because there's energy that comes from the core of planets of our size because of radioactive elements and billions of years of cooling. Okay? So it's so fascinating, this idea that we can get energy without sunlight. It broadens our perspective about how life can exist and where life might exist. Life can also grow in environments that are incredibly acidic. This river, the Rio Tinto, has a pH of 2, which is a strong acid, my goodness. And there are acidiophiles. These are organisms that love acid. Acid-loving microorganisms, bacteria and other microorganisms that actually live in the acid. Wow. Okay? Now, these types of organisms that live in these incredibly unusual environments, these environments that seem to be the antithesis of typical terrestrial, even typical marine life, are called extremophiles. Because they love, that's the phile part, they love extreme conditions. And by love it, we mean they've evolved to live in it. Okay? Here's an example close to home in the San Francisco Bay, where abandoned salt works with incredible amounts of salinity, so much salt that it's just crystallizing, a place that seems like it would just be barren of life, post-apocalyptic, the type of world that's shown in movies where the planet has died. But it's not death. It's just smaller organisms, less complex organisms, but still life. Bacteria living in those incredibly salty conditions, thriving in those incredibly salty conditions. Because there have been so many pathways of life, so many opportunities for life to go through the processes of evolution and nutrient absorption and processing to stay alive and continue to replicate. So now let's leave Earth and go to Mars. So, as we look for life, it makes sense to look on Mars. Because we see all that evidence of past liquid water, we see evidence of lakes and rivers and alluvial spreads, which is basically like a water-driven landslide. All of this on Mars. But do we see liquid water today? Well, no. We see frozen water. We maybe see muddy excretions. Maybe some muddy geysers exist on Mars. It's yet to be determined. But in the mud flats and mudstone on Mars, we can dig in and we can see that we might find something. And certainly we see that the rusting of the surface of Mars is confined to the very surface, because as we start to dig, we dig up soil that's not rusted when the atmosphere is different. But we can look beyond Mars because we haven't found anything yet there. And recently, by the way, in the news, they've talked about the potential of life in the upper atmospheres of Venus. But one particularly good place to look is the moons of the Jovian worlds, which are the gas giants. Because these giant planets, they might protect their moons because they have such huge magnetic fields. They create environments for their closer moons, which tend to be their larger moons, that allow for cosmic radiation to get redirected by those strong magnetic fields, those planetary magnetic fields. Now, you might think that's a tangent. Why would that matter for life? Well, life doesn't do great if it's bombarded by high energy particles of any type. And the stellar wind is composed mostly of electrons. But high energy particles like that can cause, well, radiation. And they can emit particles that then can cause mutations in cells. And it's hard to imagine a very stable evolutionary pathway for a planet or a moon if it's being bombarded by too much high energy particles. And so the protected moons are a good place to look for life. Now, that on its own would be a great place to start, and astronomers have thought that for a long time. But then when they look at the moons, they might find a moon that is completely made of ice, like this moon, which is a moon of Jupiter, one of the 4 Galilean moons, so called because they were discovered by Galileo. So a moon like this, which is Callisto, is completely icy, no atmosphere, maybe not a great place for life. Even Ganymede, which is the size of Mercury, just seems to be a rock. So maybe being protected by a magnetic field isn't all you need. But then you look at a planet like Io, and there's actually lots of volcanism. Now maybe too much volcanism, because although there is the energy here, maybe there's just too much hot lava for life to really find a way. It would just get burned up. But then it turns out there's a world kind of right in the middle called Europa. And Europa is icy like Callisto, but in a very different way. Instead of being pot-marked with crater marks, it's slashed with all these cuts. And that's because its surface isn't a mix of ice and rock, but its surface is solid ice and a solid ice sheet that appears to be moving and constantly being refreshed, which is why there's no craters on it. It's like a giant glacier or a giant ice sheet like the ones we have on our own South Pole or even the North Pole. And it's moving around, almost like tectonic plates, because underneath it is an ocean. Now, we haven't literally landed there and drilled down, but all the evidence, all the models of the planet say that there has to be a very large ocean that maybe encompasses the entire planet or most of it, almost like a layer of liquid water underneath a couple mile thick layer of ice. And that ocean is surrounding a core, a rocky core, that is warmed up from tidal friction with its host planet, Jupiter. So it's producing energy. And there's water. And there may be nutrients. And there may be hydrothermal vents under the ice sheet of Europa. That ocean may be teeming with life, and we just haven't seen it yet. We just need to drill through 2 miles of ice first. We need to land on the surface of Europa and drill through the ice. Well, it's an ambitious mission, but maybe it's one we'll do. Right? Here's Europa again. But there's a moon that's even more exciting than Europa. Perhaps. Yeah, almost certainly. And that moon is called Enceladus. Now, Enceladus isn't around Jupiter. It's not one of the Galilean moons. And honestly, it was much less well known as a potential planet of life until rather recently because of the Cassini space mission, which was a many decades-long space mission to orbit Jupiter and collect data. And Cassini found that this icy moon that certainly has some similarities to Europa, although it's much smaller, Cassini found that Enceladus seems to actually have in its there's ice, its sub-ice ocean, the thermal vents. Those same ones that foster life here on our planet, devoid from the energy cycle of photosynthesis from the sun, completely separate, but completely alive, even with complex organisms like crabs here on Earth. There's hydrothermal vents on Enceladus. Enceladus is warm enough. There's evidence of some molecules coming up out of those vents. Nothing that's directly pointing to life, but it's really exciting stuff. So maybe we have it. Maybe we have crabs on Enceladus. But we gotta confirm it, right? We have to actually go back to that world, send a mission back to confirm. Because this is all stuff that's happened in the last few years. Discoveries, revelations. Okay? Now there's one more fascinating moon, quite different, in our solar system. And that's Titan. Titan is also a moon of Saturn. And Titan is much bigger than Enceladus, by the way. Closer to the size of Ganymede or Callisto, going back to those Galilean moons. And Titan is a very unusual moon. It is the only moon that has an atmosphere. For whatever reason, Titan was able to hold on to an atmosphere and kind of go through a positive feedback loop. But once it got an atmosphere, its atmosphere is allowed to get thicker. And just at some critical condition, it's the only moon that has one. A real atmosphere. And just to put that in perspective, in our own solar system, the only other planet that has an atmosphere is Venus. And Venus's atmosphere is so thick, so dense, that it's the opposite of what you want for life, unless perhaps there's life that lives on the very top, almost like on the top of an ocean. But regardless, that's it. There's just Venus and Titan. Mars doesn't have an atmosphere to speak of. Okay? So other than Earth, just Venus and Titan. So Titan's atmosphere, however, is very different because it is such a cold world. Its atmosphere is actually composed of clouds made of half-frozen methane and ammonia. Basically, on Earth, methane and ammonia are such light elements that they would never form clouds. Instead, we have clouds made primarily of H2O and dust particles. But on Titan, it's dust, methane, and ammonia. And that methane and ammonia actually rains. There's actually storms on Titan with ammonia rain, lakes of ammonia, erosion. It's a world with weather. But the weather isn't made of clouds of water, but instead of ammonia and methane. So we certainly have the energy. We've got a full water cycle-esque phenomenon, but instead it's ammonia raining down, washing through rivers, collecting in lakes and small seas, then evaporating back up. Processes like that create opportunities for life to form because that flow of nutrients and that flow of energy could give the possibility for life. Now, the issue is there's no water. So remember, I said one of our building blocks of life is water, but Titan doesn't have it. So then theoretical biologists. Sometimes, if they specialize in the possibility of life in other worlds, they might call themselves theoretical astrobiologists. They speculate on whether you could actually have a pathway of life that didn't rely on water. Could you form cell walls and cell membranes entirely from the available chemicals on a world like Titan? And perhaps there is a way. Perhaps there are some type of microbe that lives there on Titan. We really don't know. And there's so much yet to know in our own solar system because it's a vast space. But if we're talking about vast space, the space beyond our solar system boggles the mind. As we've talked about, the distance between stars is so incredible. The entire solar system, well past Titan, if on a scale of a college campus, would have its next neighboring solar system across the United States in New York, if that campus was in California. And in between is just empty space. But we have neighbors. We have neighbors like Alpha Proxima, our closest star that neighbors our sun, and lots of other stars within a few light years. And those stars have their own planets that we've discovered, exoplanets, so many of them. But can we gain enough information from those exoplanets to determine that maybe they have life? Maybe there are actually Earth clones out there, rich planets full of life, teeming continents with jungles, but completely alien to ours? Well, how would we know? Because even here, an image taken by the Voyager 1 at the edge of our own solar system, Earth just appears as a tiny little 1-pixel blue dot. When we look at exoplanets, we can't get them to resolve even in pixels in 99% of cases. Instead, we just have to have indirect evidence of them as they affect the star that they orbit, sometimes affecting the light when they eclipse the star, otherwise just tugging on the star. Such indirect ways we have to measure these exoplanets. Could we actually gain enough information about exoplanets to determine that they might have life? Well, maybe, because we can look at the emission spectra from a planet. Because a planet's a black body, and it should emit a complete curve of light corresponding to its surface temperature. But if it has certain chemicals in its atmosphere, then we should see absorption lines in that otherwise continuous spectrum. For example, if we look at the absorption lines here on Earth, we see clear absorption lines for H2O, C2O, ozone, okay? Carbon, so obviously C2O or CO2 being carbon dioxide. All right, I said C2O, I meant to say CO2, but then O3 is ozone. So we see these really telltale absorption symbols for life. Now, if we were to look at a spectrum like this for an exoplanet, it's going to be much fainter. We need better telescopes, but maybe we'll develop those. We already are. We made incredible breakthroughs in the way we can detect very, very faint signals and the computational power to actually analyze those very, very faint signals has been real innovations. So maybe we'll really be able to find a planet that has such compelling evidence in its spectrum that we say, wow, there must be an atmosphere rich with ozone. There must be an atmosphere rich with oxygen. That sounds like an Earth-like world. But even then, that's as far as we could ever go because we can't get there. It would take hundreds of years in the best case scenario to get there. So maybe we should send radio messages. Maybe we should communicate with aliens. And we've tried a bit. We've sent out in these Pioneer space probes, which are space probes that were given enough velocity to permanently exit the sun's gravitational pull. They're on trajectories to leave the solar system permanently. We sent little plaques made out of sturdy metal or a record made out of metal that tell a story about humanity. Now, this is kind of almost a forlong, sad thing to do because these plates, if they ever do reach another star, will have to travel for hundreds of thousands of years. Will humanity even be around in hundreds of thousands of years? So if these are ever found by an alien species, perhaps we'll be gone, having destroyed ourselves or been destroyed by a comet collision or something. And this will just be our one record, picked up by an alien species 1.5 million years from now, for example. Who knows? But most likely they'll just float through space and never be found again. So it's an attempt, I guess. We're sending something off to never return. But will it ever be found? Will our story ever be told? Is there anyone to tell our story to? Well, Back in the 1960s, I would say 70s, but back in the 1960s, astronomers started to really take this idea of looking for alien life seriously, and this is around the same time as sending out the Pioneer probes. And they started to do it with more than just probes, but actually looking at things that travel quickly, light, and looking at radio waves. And they started to scan the heavens, scan the sky, the celestial sphere, for signals. Perhaps aliens out there were trying to communicate. Maybe they're sending out signals. Or maybe they're inadvertently spreading radio waves out into space that we could pick up. But we haven't detected anything yet. We look at stars that seem like good candidates for life, and certainly now, since the mid-1990s, we can look at stars that have exoplanets that are in the right distance, the habitable zone, the Goldilocks zone, which is the right distance from a star of particular intensity in order to support liquid water. But we still don't see any radio signals. Not yet. We've never picked anything up. We've never seen an alien saying hello. But even if we were to pick up a signal, that doesn't mean that we're suddenly tied in with another alien species, because think about the communication time. If we pick up a signal from a star that's even just 20 light years away, which is incredibly close by stellar neighborhood standards, that's in our immediate neighborhood of stars, then it would take 20 years to respond to that signal. We could get it and analyze it and say, look, this is not a natural phenomenon. This is actually some sort of artificial communication here. This is made by intelligent hands. We can listen to it, get our linguists working on it to try to understand, decipher it as a language. You can imagine that process. It would be amazing. And then send a return. Say, hey, we listen. We realize you're there and we're over here. But it would take then 20 years for our signal to get back to them. So talk about slow communication, right? But maybe more likely at 80 years. So, but the search continues because it would be an incredible starting point. And one of the big organizations that uses radio waves to search for extraterrestrial life is SETI, which just stands for Search for Extraterrestrial Intelligence. Okay, that's what the acronym stands for. And as we search for that extraterrestrial intelligence, we have to wonder, should we be sending out signals? Because although we do release radio waves into space, they're rather weak, and they would be incredibly attenuated, which means reduced in power by the time they reached stars in the 20, 30, 40 light year range in our neighborhood of local stars. And maybe they'd be too hard to detect, or maybe those aliens have better detectors than us, if there are aliens out there. So then maybe we should send purposely really strong signals, build giant transmitters, and send out really strong signals directing, saying, hey, here we are. Or if we even pick something up, if one of these radio telescopes picks up a signal, then we should respond right away, maybe. Or maybe we shouldn't. Maybe that's a bad idea. Maybe we don't want to open ourselves up for invasion. But then again, wouldn't the invasion take hundreds of years? If aliens can't travel faster than the speed of light, which is the golden rule of physics, right? Such interesting questions. No obvious answers. Do we want to be alone? Is it better to be alone in our little solar system, relatively safe? Or should we open ourselves up? I don't know. There's no clear answer there. Now, we've talked so much about life outside of Earth, and it's so fascinating because hopefully I made a good argument about how life is so incredibly tenacious, that we see extremophiles that are so extreme. And we see so many opportunities for life just in our own solar system, on little icy moons and strange atmospheres with methane clouds. And so we think of all those exoplanets and all that other life, and it seems like there just must be life out there. But we haven't discovered it. But then again, we've only been looking for 100 years, right? Think about, modern society, actual telescopes, even radio waves. None of that stuff's very old. So maybe we're just not patient enough. But it does beg the question. If there's so many opportunities for life out there, so many stars with so many planets around them, why isn't there some complex organization of life, like in the sci-fi movies, that spans the stars? Is it just because stars are too far apart? Is it just an impossibility? But even then, at least there should be little islands of life like our own. So to sort of think about this in a quantitative way, there's a famous equation called the Drake equation. And the Drake equation speculates on the number of basically life forms out there. So the idea is that the equation n would represent the number of basically intelligent life forms out in space. So maybe in our own galaxy, if we start there, right, a good starting point. So there'd be the number of intelligent species like ours that have a civilization that are aware of themselves and aren't, just microbes. So we think about how would we calculate that? Well, we look and we can say that our star, the first term, and the star here just refers to the subscript, our star is the rate of formation of stars like the sun in our galaxy. Okay? And so we can kind of get an idea about how many stars there are that are being formed that are just the right kind of star. Because certain stars seem particularly bad for life. There's no way one of these hot blue stars that only live 200 million years could ever have planets to support life. There's no way in any understanding of evolution it could be completed in 200 million years, right? And even then, it certainly couldn't be a civilization that would form in such little time. So we need stars that are the right type. So this is the rate of star formation. Well, then we go and we say, okay, well, how many of those stars that are being formed, that are the right type, have planets? So F is the fraction with planets. And then N is basically the number of the fraction that have planets that have inhabitable planets. So this is the fraction with inhabitable planets. And then the next term is the fraction of habitable planets that actually support life. Well, these ones we could kind of look because we can do our surveys of exoplanets, but this one is just a wild guess because we only know of one. Okay? So this is the fraction, the L there would represent life, fraction with life. And then there's the fraction with intelligent life. And then there's the fraction that of those ones that have intelligent life, where those intelligent life forms built a civilization. Because maybe there's intelligent life that just never goes the civilization path. And if they never go the civilization path, they're never going to build radios. You could think of maybe animals on Earth, like other primates or dolphins, that may be intelligent, but just never built a civilization. So when you put all those terms together, then you come up with a multiplication of, well, one more term, how long they live. Let me talk about this one real fast. Because this last term, L, would be once a species has a civilization, how long does it actually last? Or do civilizations tend to wipe themselves out? Do they learn technologies that are so powerful that they can't handle them? Or are there just too many stray comets and asteroids that worlds just get blown up? Well, that's an interesting thing to consider. So look at the way this equation works. We take each of these terms, which are all fractions, so they could all be between 0 and 1. They're all probabilities. And we just multiply them together. So we multiply one probability by another, by another, by another. And that gives us the total number. Okay? So you start with a number, which is the rate. So it's a number of stars, and then everything else is fractions. So what you're left with, once you multiply the number of stars by all of these fractions, some of which are just wild guesses, because again, we only know of one planet that supports life, then you come up with the total number of planets that would have civilizations that are still alive. And the number can either be very small, depending on, and this is kind of unsatisfying, depending on how you choose these fractions that are wild guesses, or it can be incredibly large. So with certain considerations, if you assume that certain things are incredibly likely, like all civilizations tend to wipe themselves out, and civilizations themselves are very rare, well, then you could have a case where maybe there's only 2 or 3 stars per 100 billion stars that foster a current living civilization. And if that's the case, our galaxy is so vast that there's only 2 or 3 aliens like us, then we may never meet each other. On the other hand, if you make other assumptions that that civilizations are a lucky thing, and once you get a civilization, you start spreading to other worlds, and then species tend to keep themselves alive, they become tenacious, then maybe there's a lot more life out there. And maybe there's lots of intelligent aliens with spacecraft and multiple colonies on multiple worlds, and maybe even generation ships that travel between stars and that sort of thing. Well, in that case, maybe there's tens of thousands of intelligent aliens in our own galaxy. The thing, though, is that even on those higher estimates, those big values of how many intelligent civilizations there might be in our own galaxy, they still could be fairly spread apart. Because again, our galaxy is 100,000 light years in radius. It's so vast. So maybe they're just hard to find. Maybe they're kind of all like us, just stumbling around in the dark, kind of looking for other intelligent life out there. But you do wonder that if we came along and we've advanced so much in just a few hundred years, what if we had evolved, say, just 10,000 years earlier? What if we had built our first cities instead of 10,000 years ago, 20,000 years ago? Because the very first cities that archaeologists discover in the Middle East are about 10,000 years old, right? That's when humans developed language and started farming and had agriculture and actually started specializing and so on. This is the story of how we got to be here we are today, right? So what if that all had just happened a little bit sooner? And right now we were sitting in a world where we had space travel for thousands of years. Well, wouldn't we continue to advance? So it seems that since that's such a small amount of time in geological time and astronomical time, a few thousand years difference, then there could be civilizations that are much, much more advanced than ours. And if that's the case, maybe they're doing things like building giant rings around stars as the perfect structure for fostering life, and rearranging planets and blowing up planets to recycle the minerals from their cores, and these incredibly large scale engineering projects. Because wouldn't a super advanced civilization have such things? And if that's the case, there should be evidence of that. There should be evidence of super advanced civilizations' megastructures, structures that are the size of solar systems. And I know that sounds incredibly fanciful, but again, in astronomical time, there should be civilizations that are much more advanced than ours. So we actually look for that sort of thing. We use infrared telescopes to actually look for the heat signatures that would come from megastructures. But we haven't found any. So I guess we'll leave it there. We search for life. It seems so likely to be out there. But here we are in 2020, and we haven't discovered it. What does that mean? Maybe we are just truly alone. All right. Well, thank you so much for listening to this lecture. I hope it has been very interesting and informative.